Hello everyone. We have been discussing about mode locking techniques and all, and in the last class we looked at one of the techniques that is that can actively mode lock a laser, a continuous wave laser. Uh, Before I proceed further, I must tell you something at this point, that the concept of mode locking is extremely intricate, and in this course what we are doing, we are looking at the basic concepts of this particular technique. If you want to learn a bit further, particularly we didn't go through the detailed mathematical uh, derivation of the conditions for mode locking and all these things, but these are all there in the references that I suggested, and also these are available in literature. So if you want to go through the detail of this technique, please go through those references. So as we said, we will keep it to a basic fundamental level only in this particular course. All right. So let's come back to what we are discussing. So we showed by using acousto-optic transducers, one can achieve mode locking, and that is an active mode locking. Why? Because you are actively controlling the modulation inside the laser cavity, modulation of the amplitude or frequency, whatever you are doing. So are there other kinds of active mode locking? The answer is yes. It is not only that acousto-optic modulator has to be used, or only acousto-optic modulator can generate mode locking of continuous wave lasers, but electro-optic modulators also can do the job. For example, a Pockels cell can do the job of modulating the amplitude of the laser light, and thereby give rise to mode locked pulses. And both these techniques, acousto-optic modulation as well as this electro-optic modulation, are used in real life. Now, other than this active mode locking, what else do we have? So we have also something called passive mode locking. We have seen another passive pulsing technique called passive Q switching. And what did we do there? We just used a dye solution or any other thin film which contains some material which is known as saturable absorbers. Here also, in case of passive mode locking, the technique uses a saturable absorber, which are mostly some dyes, like we mentioned about cyanide dyes in the earlier cases. Okay, so there are different materials available for which are good saturable absorber. So let me remind you what saturable absorption is. If you take this material which we call as saturable absorber and send in light, so it absorbs all the light going through as long as the intensity is low. As the intensity of light is increasing, that is, I am increasing the number of photons coming in, then it will reach a condition of saturation, which means the population of the excited and the ground state will become equal, that is N2 equals to N1, and at that condition there will be no further absorption of light in practical sense. Thereby the system will be called a blitzed system. So in this blitzed system, the light will just pass through. So light will, so the medium will behave like a transparent medium to the light. So once earlier at the low photon intensity, this dye is opaque. At a sufficiently high intensity beyond a threshold, this becomes transparent. Okay. So that is what is the function of the saturable absorbers, and in the passive mode locking also we use a saturable absorber dye. Now how you can implement this saturable absorber to do the mode locking. There are various different designs of doing this are available, but whatever be the case, this saturable absorber, which is a dye, is definitely a part of the resonator. So it has to be within the resonator, and that is why, so we put the resonator this dye inside the resonator, and I forget about it, and the dye will do the work, do the job by itself. So I am not going to do anything, and that is why this method is known as a passive method, just like passive Q switching. So here I have shown one picture of the cavity involving this saturable absorber. So the dye cell is right here. So this is my dye cell, and this output mirror, and this is the high reflector, and then you have the active medium. So this is dye is within the resonator cavity. Okay. So in this particular configuration, this saturable absorber, which is a dye, along with this rear mirror, that is this guy, they are combined to reduce the number of reflective surfaces in the laser cavity and to minimize the unwanted losses, right? Because if there are gaps and all, then there will be multiple reflection between the the container surfaces and all these things. So we will have unwanted losses, which we really don't want. So they are kind of almost coupled together. Fine. So the end of the so if I can imagine it in a way like I have a container whose inner wall is a high reflecting mirror, and then I have this dye solution inside. So I minimize the loss in that case. Now let us look into the detail of this passive mode locking, how it works. So first let us assume that I have an absorbing dye, and it has let us assume it like a two-state system given by energies E2 and E1, and let us take small omega is the frequency of one of the longitudinal modes of the optical cavity. There may be n number of modes. Let us take one mode which has a frequency small omega. Okay, so this is I know. This we assume now. Now suppose the excited state of this saturable absorber dye has a lifetime tau given here, and this tau is of the order of the magnitude of the cavity round trip time. So what is the cavity round trip time? That is given by the period capital T given by 2L by C. So if I have such a system for which tau is having similar value as that of capital T, then what will happen? A few nanoseconds in a typical resonators, the dye molecule will just act like a passive Q switch, and we have seen this one in case of Q switching. On the other hand, if this dye lifetime, excited state lifetime tau is comparable to the if it is very short, how short? If it is comparable to the pulse width of a mode locked laser output. So that means that I want to achieve a short pulse, say 100 femtosecond or say like 1 picosecond, and I am saying that if this excited state of this saturable absorber dye has a lifetime of say like 1 picosecond, then I can achieve mode locking. You try to read between these lines here. Here I am imposing a condition which will which deals with some time scale which is equal to few femtosecond to picosecond, which can be also the gap between the two modes. Now, so as we have already assumed that we have two state systems, and okay, so this E2 minus E1 essentially, if I write it in terms of omega, then I must have H cut omega. Now, this light in the optical resonator, which is arriving at the cell mirror. Cell mirror is that I said that dye is taken in a say rectangular container, inner side of which one of the inner sides of this container is a mirror. Okay, and this cell mirror promotes some molecules from the lower level E1 to the upper level E2, causing the losses in the light intensity as a result of absorption by the dye. Fine. Now, this is at the beginning. Okay, so at this point, like at the beginning, when the pumping just starts and you start getting some photons coming down due to spontaneous emission or maybe little stimulated emission, till the time I have not achieved gain. Okay, so the intensity of light coming is very, very small. So the laser gain cannot overcome the loss that is incurred at this dye, because dye absorbs and goes from E1 to E2. Okay, so till that point when I do not have the condition where gain is more than the loss at the dye, I have no phase relation between the different modes oscillating. So the result is again a chaotic output. So there will be random interferences, and I will have a very low intensity light, and they are totally uncorrelated in terms of phase. They are not synchronized. Okay, so that is what we will get. Now, this will not remain the case forever. Okay, after some time there will be more and more photon coming in, and slowly the gain will overcome these losses. Now, beyond this threshold, the light amplification in the resonator, it will approach the saturation intensity in the dye. What does that mean? That this two states 1 and 2 in the dye. So from E1 to E2, it is continuously going, more and more lights are coming from the active medium. So there will be a condition when this population here N1 will be equal to the population here N2. So N1 equals to N2, and this is saturation, we have just mentioned it. So when this happens, the gain in the laser medium is still not increasing very rapidly. Okay, so this is still in a linear regime, that is slowly increasing. The gain is slowly gearing up, but still not in a very abrupt way like non-linear way. Okay, but the absorption of the dye, it becomes non-linear. Okay, then what happens? More and more photon coming in, that is intensity is higher and higher. The substance, that is the saturable absorber, undergoes saturation. So we reach a condition of bleaching, and once this happens, the dye becomes transparent to the incoming light. So once it becomes transparent, it will no longer incur loss to my cavity, rather it will allow the light to propagate through the along the axis of the laser cavity, and it will create the amplification of the gain, and the laser gain which was following a linear relation with time, now it will become non-linear. So, it will rapidly increase. Okay. So, now the intensity is extremely high and the amplification in the medium becomes non-linear, right. We explained that, and the dye molecules now return to the ground state after time tau. Okay, sorry, you missed that. So, after its lifetime it comes back to the ground state, and then we repeat the same process. So, what we do, we first make it opaque, and then at a particular threshold value it becomes transparent, and I have extremely high gain, and I get a laser output, and after its lifetime the excited dye molecules will come back to the ground state. Again it will be opaque to the incoming light, and again after some time it will be transparent. So, this process will keep going. So, I will get a repetition of pulses, and these pulses will be shorter and shorter and shorter. So, we will summarize this process of this passive mode locking. So, essentially it has 3 main steps. The first one is the linear amplification and linear dye absorption. So, linear amplification in a sense that the active medium will generate photons, okay, and that will be a linear function of time, and at that particular condition dye also will keep on absorbing in a very linear way. So, that is my first step. In the second step, the dye starts absorbing more and more photon, okay. So, that is in a non-linear fashion, and in the third step the dye gets totally bleached, and my amplification becomes highly non-linear. So, the amplification is extremely high, and then I get the pulsed output from the cavity, okay, and then this whole 3 steps again repeat, okay. So, they are again repeated, and you get more pulses after a certain time, and which is more or less governed by this lifetime of this dye, okay. So, these are the main techniques that are involved in mode locking. Apart from this one, there are other type of techniques. One of the important thing is called Kerr lens mode locking. So, okay. So, that also is used quite a lot in the practical system, where this phenomenon of Kerr lensing is used to modulate this amplitudes of the laser longitudinal modes, and ultimately make a a single pulse oscillating in the cavity and getting a very short pulse. So, I think we have covered the pretty much basic of all the pulsing techniques that are existing, and with this knowledge, what we will do, we will go and learn about some specific lasers. Okay. All right. So, what are the different types of lasers that we can come across, or what are the existing different types of lasers. The number is really huge. Now this lasers can be categorized in different sections. I have tried to categorize them in the following manners. There are lasers where the active medium is essentially some solid state materials. There are specific materials which are semiconductor in by nature, so we can have semiconductor lasers. There are lasers whose active medium consists of atoms or gaseous ions. So when we are having just atoms, they are of course in the gaseous medium, because non-interacting atoms will be always in the gaseous phase. So we can also make lasers out of gaseous molecules acting as the active medium. We can form lasers utilizing a chemical reaction. So a chemical reaction mixture can act as the active medium, and the corresponding chemical lasers we can get. And there are certain lasers which are operated in the so called liquid states. So for example, like dye laser, it is not very fair to tell it like liquid medium, but since the host medium for this dye molecules which provides the states for laser action are dissolved in some solvent which are liquid. Okay, so these are the basic categories of lasers that I have put together, but no way this is limited by the categorization that we have done here. Now certain lasers under these categories we will look at. For example, we will look at ruby laser and ND arc laser and Ti sapphire laser under the solid state laser category. We will look at certain semiconductor lasers, okay, and among the atomic and ionic gas lasers we will look at helium neon laser, which is like one of the most widely used continuous wave laser. We will look at argon ion laser, we will look at copper vapor laser. Under the molecular gas lasers head, we will look at carbon dioxide and nitrogen lasers. Under the chemical lasers, we will talk about iodine lasers, and one of the very unique kind of laser which is known as excimer laser. And of course, we will talk about detail regarding the dye laser configuration. Now, before going further into the detail of these things, can I pick any given material and use it as a laser active medium? The answer is no. It has to fulfill certain criteria. So if you recall the very first weeks of or the second week of classes, we dealt in detail about the requirement of like 3-state system or 4-state system which can give laser action, but not necessarily if I have a 3-level or 4-level system it will always give laser action. It has to also fulfill the criteria of their their lifetimes, the excited state lifetime. So it should be extremely suitable so that ultimately one can achieve population inversion. For example, like when you say ND-YAG laser, so YAG means yttrium aluminum garnet, so it's a substrate. Now this yttrium aluminum garnet as such cannot give a laser action, so you try how much you can, but you cannot achieve laser action at any frequency of that material. it is the neodymium ion which gives the necessary electronic states that can give rise to population inversion, and thereby you can get the lasers. So, it is very much essential to find out which particular material or molecule or atom or ions has the required electronic states that ultimately can give rise to population inversion and hence laser action. So, in the following class we will go through different types of lasers, we will look at their electronic structures, which particular electronic states are involved in lasing, why, some little bit in details for certain lasers and on. So, we will stop here today, and thank you for your attention.